Hello everyone. In this video, I am going to discuss microwave bandpass filter based on naturally coupled transmission line. So I'm going to start. So first of all, for every design, you need to determine the order of the filter. It doesn't matter it is low pass filter or bandpass filter. Unfortunately, there is no textbook formula for obtaining the order of a bandpass filter directly. But there is a way to obtain the order of the bandpass filter. You can do it by transforming the bandpass filter to its representations in low-pass domain. The process of these transformations involves mapping of corner frequencies to the low-pass domain. So I'm going to show you, the figure is not on the right here. I have to change the wording. So here is the technique. The bottom graph here represents the bandpass filter, the characteristic of the bandpass filter. The upper ones represents the characteristic of the low pass domain. Is the filter characteristic equation is still based on. Okay, I should say this. What you need to do is to move the whole passband leftward. Move it until you achieve this. So in this case, what you would do is you make sure the resonance frequency is matched to 0 here. And you make sure the higher corner frequency is matched to omega p. And you make sure the stop band frequency is matched to omega s. And on the other hand, this side, the lower corner frequency is matched to minus omega p, assuming that the filter characteristic is completely symmetrical about the vertical line passing through the omega naught. Yeah, obviously, this omega s palm is matched to minus omega s. So we are assuming that this is symmetrical, but we move the whole complete graph leftward to the left, I mean. So what we need is a formula. So let's suppose the frequency in the bandpass domain is omega, and the frequency in the low pass domain is the capital letter of omega. So what we need is this formula. Omega is 1 over delta and then times omega bracket. Omega divided by omega naught and then omega naught divided by omega. Omega naught here is the center frequency. Center frequency means the resonance frequency. Delta here represents the fractional bandwidth. The fractional bandwidth is given by the width of the passband divided by omega naught. The center frequency is given by square root of the product of corner frequencies. I mean, the upper corner frequency multiply with the lower corner frequency and then take square root of the whole products. So this is the formula that we constantly use in filter design. So let's try this. Let's try to substitute the formula with omega equals to omega naught. And in this case, this become omega naught and this will become omega naught. And omega naught divided by omega naught is always 1. And omega naught divided by omega naught is also 1 on the left term inside the bracket. So 1 minus 1 is 0. And let's try the upper corner frequency. You put it there, and then after plugging in, then you do a little bit of manipulation here. You multiply the top and bottom by omega naught. So this is what you are going to get. The top will be omega h, the upper corner frequency times the lower corner frequency. The bottom become like this. Then in this case, omega h can be cancelled with omega h at the top can be cancelled out, and the omega naught at the bottom will also be cancelled out. So as a result, you got this. So this is the bracket term is obviously the bandwidth. So you got 1 here. Okay. So in other words, if you are going to match the stop bound frequency, then this is what you are going to get. Of course, we don't know the exact value until we have the number for this. It's not possible to further simplify this because omega of S is another unknown. So if you consider the low pass domain of the bandpass filter, you will discover, right, we have 0 here and the pass band is 1 and the stop band is capital letter omega S. And here is the roll off. The slope of the roll off here determines the order of the filter. Normally, the steeper the slope, the higher order you will need. So what we need to do is to use this formula for Butterworth bandpass filter. This is just the textbook formula. A of S here represents the gain, the gain in dB for the stop band, while A of P here is the gain in dB at the pass band. Normally the gain at the pass band is 3 dB. Minus 3 dB. I'm now talking about the gain, not the attenuation. The gain at this one is minus 3 dB because the gain at the top here is 1. So the gain at the stop band here will be given by the question, most likely. So for trapezius bandpass filter, you need to use the. By the way, the formula here. The formula here is for low pass filter, determining the low pass filter, the order of the low pass filter. But we are going to use it for bandpass filter design. Okay, let's take a look in the Trapezoid filter. The formula that you need is this one. Again, this formula is originally intended for determining the order of a low pass filter, but you can use it for determining the order of the bandpass filter. All we need to know is the roll off, the characteristic of the roll off. Okay, now let's take a look at the basic architectures of a bandpass filter. I can tell you that one that we learned is going to be the laterally coupled line bandpass filter. It's like this. This is the one. So in the field of microwave, right, you will be surprised. The bandpass filter is just a combination, a series connection of all these parallel segments. So you have got one parallel section here, the other parallel section here, the other parallel section here. Yeah, that's so on. Yeah, this is the most conventional version of the bandpass filter. Okay, so the unit that you need to construct this bandpass filter is this parallel line sections. So coupled line bandpass filter can be implemented by collecting multiple coupled line sections in a manner as shown in Figure 1. This filter can be either Butterworth or Trapezoid or any other topology known to the academia. So the basic unit is just the most fundamental unit is the coupled line segment, so-called the unit cell here for this design is a coupled line segment. It's just two parallel lines. And you leave this open circuit and you leave the opposite end open circuit as well. In another line open circuit. We only use one of the port here, the other port of here. We make sure the open circuit is done in a diagonal manner. So this is the coupled line. By the way, the length of this line should be 90 degree of the resonant frequency. The resonant frequency is the center frequency. Okay? So let's take a look at resonance. Each coupled line segment produces a resonant response that contributes to the whole filter frequency response. At low bandwidth filter normally require low coupling. So this means, by the way, when the resonator has low coupling, this means the separation between the upper lines and the lower lines are wider. This is usually used for narrow band filter design. On the other hand, if you want the bandwidth to be wide, then most likely the coupling has to be high. This means the upper parallel line, the upper line segment and the lower line segment are very close to each other. Mathematically, each coupled line segment can be modeled with this circuit. Now, first of all, the upper line and the lower line are exactly the same. It's just a line with the characteristic impedance naught, and we don't assume the length of the line is 90 degrees for the time being. We just assume theta. Theta is close to 90 degrees. Now you have two coupled lines. Here inside there is a gap. The gap can be uh, modeled by this inverter. It will cause minus 90-degree phase shift. And the bottom, the transmission line here, is represented by this coupled line. So this is the equivalent circuits of a coupled line section. The ABCD parameter of each of the transmission line segment can be written as this in this manner. And this is just a conventional formula for the ABCD parameter for a transmission line segment. You need to know the characteristic impedance, and also you need to know the length of the line, beta L. Beta L is theta. Okay. The gap between the upper line segment and the lower line segment can be modeled as a inverter. The inverter is actually the gap of in the coupled section, coupled line segment. And it can be modeled as an ABCD parameter as well. So the whole coupled line can be a cascade of three blocks: the upper transmission line and the lower transmission line, and the middle one is the gap. The gap is represented by this. Yeah, the diagonal matrix is 0. This means this always match. But the other element inside the coupled line is ABCD parameter is like this. Minus J, the small letter J here represents the square root of 1, while the capital letter J here represents the admittance constant. The admittance constant depends on the coupling and the characteristic impedance of the line. Yeah, the separation of the lines determine the couplings. Okay, now if we expand, if you don't mind algebraic manipulation, right? You expand this matrix and do a bit of calculation, yeah. Then you will get this. You will get the sum for the diagonal matrix, and you will get also not the sum in the other element in in B and C. Yeah, it's not the same. So what you need to do now is to find out the image impedance. The coupled line has an impedance, and this characteristic impedance is called image impedance. So it's similar to Z0 in the ordinary transmission line, but it is called image impedance. And to calculate this image impedance, yeah, you just do square root of A times B and then divided by C times D, yeah. So you do this, and then here you cancel off, so you get only this term and this term here. Now the center frequency occurs when theta here become 90 degree. So if you put 90 degree here, all the cosine 90 degree terms will be 0. So you don't have this, so you get only this. Then obviously what you get is J Z naught square. Z naught here represents the characteristic impedance of one individual transmission line on the top and the bottom. and C naught square. Yeah. Uh, and when you have a coupled structure, it's always easy to determine the characteristic impedance in terms of even mode and odd modes. The even mode represent, yeah, as I explained to you in another slide, even mode is the condition where the voltages at, uh, at the lower end are completely equals. I mean, at the left end, uh, both line segments, the left end of both side segments are equals. And if you talk about the odd modes, this means the left end of the transmission lines are opposite in sign. So this is also so-called the even mode, odd mode. Now, uh, we are going to use this formula to find out to calculate the image impedance. So let's take a look in the propagation constant. The cosine term here can be used to find out the A is cosine beta. Yeah, if you want to know the propagation constant, cosine of the uh, beta L, you can use the parameter A to calculate this. Uh, Beta L is exactly equal to beta. So you have this term here, and this term is actually equal to uh, the sum of even mode characteristic impedance divided by the difference of the even mode characteristic impedance. So altogether, you have two equations. Now this one first, we cancel out and then we got this. So if you solve equation A, 4A, and equation 4B together, yeah, equation 4A and equation 4B are two equations with two unknowns. They are the simultaneous equation, and you can just solve it for the even mode impedance and the odd mode impedance. And surprisingly, the final equation is that simple, very similar. The only difference is the plus and minus sign here. Okay, for the odd mode, right, yes, minus, and so you can expect the odd mode impedance to be slightly smaller. The even mode impedance is slightly higher. Okay, so now let's move on. Each of the line segments in the bandpass filter has odd mode and even mode and impedance. The odd mode impedance and the even mode impedance. And equation 5a and 5b allow us to calculate the value of Z of log E and Z of log O for each line couple line segment. We have to do it for each of the segment individually. So to be able to do this, we need to know the value of the J Z naught. J here is the emission constant. It represents the coupling of the transmission line. Okay, before doing anything, right, we need to know the formula. Yeah, we already know the bandwidth formula. So what we need to do is in the leftmost term or the rightmost term, we use this formula to calculate the Z0 J of 1. Yeah, you just use square root of this. This is just the same formula that we used for the designing the lump element bandpass filter. And for the other terms, then you use this. Yeah, the square root yeah, pi omega divided by 2 here. Yeah, the square root uh, is for the gain, the filter gain. The previous stage and this one. Okay, and the final one will be the same as the previous one. So it might look very difficult, but I can tell you, you don't need to do the calculation for all the terms, all the segment. You only need to do half of the segment. The J of IN here represents the characteristic admittance of J inverter. Actually, the admittance constant. Y naught here, Y of naught here is the characteristic admittance of the connecting transmission line. Yeah, let's move on here. We don't need to know too much. We just need to know this E formula together with the formula for finding out the even mode and odd mode impedance. So what we are going to do is to calculate this, and then we determine the even mode impedance and the odd mode impedance of each of the parallel line segments. Now the methodology has already been discussed. I have already explained to you how it works. Now let's go through an example. Suppose we have a buttermouth coupled line bandpass filter. The center frequency is 5.7 gigahertz. The bandwidth is 300 megahertz. The upper corner frequency minus the lower corner frequency is 500 megahertz. At I make a mistake here. It's 6 gigahertz. Okay, I will correct it. I should say 6 gigahertz. I need to correct it. This one. This will be 6 gigahertz. Because okay. So first of all, okay, we are going to start again. At 6 gigahertz, the attenuation should be at least 20 dB. So the filter is expected to be fabricated on a 15 mil Roger toroid YAA0 substrate. It's very easy, this discussion, right? So I'm going to go through it. So first of all, you need to find out the fractional bandwidth. The fractional bandwidth is the actual bandwidth divided by the center frequency. So this is the way, 300 mega divided by 5.7 giga. So you get this, about 5%, 5.26%. The next thing that you need is the order of the filter. So we already know that the passband frequency is always at 1, yeah, 1 radian per second, yeah, in a low pass domain. Now we need to know the low pass domain stop bound, and this is the formula we have learned. Now let's substitute the frequency here. Yeah, 6 gigahertz divided by 5.7 and the bandwidth. And by calculation, we got 1.95. So it makes sense. This value has to be larger than 1. So now we are going to use the Butterworth formula to determine the order of the filter. This is the formula. And this value is always 1. And this value is 1.97. And this value is always free. Actually minus free, because we talk about the gain, minus free. And this one, as previously done, is minus 20. So as a result, we got this. Yeah, the minus as I got minus and minus become positive. We got this. Okay. And after the calculation, you get 3.44, and always round up to the integer, not round down. Yeah, do not round down this figure. If you round it down, then the order become 3, then it will be incorrect. You have always round it up. It doesn't matter whether it's Butterworth file filter or temperature filter, round it up. So from the table, the Potota table, we got the G values here, the filter gain at each stage. And originally, this is the table for low pass, but we are going to use it for high pass. So bandpass filter. Now, what we are going to do is to calculate the even mode and odd mode impedance. So for the first stage, we got this. The formula for the first stage is like this, and the rest, the end stage, it will be the same. You don't need to do calculation, you just copy. And the rest of the filter element will be based on this formula. And you just plug in with the filter gain, this 0.767 is here. And the previous one, I mean the present one, the previous one. And then you will calculate. You get this. This one, right, we just copy. Yeah, they are the same. You can see this here. They are the same. And the middle one, this is the final one. You get this. Now, you have already got the Z0 J1 value. The next thing that you need is to use this value to calculate the even mode or odd mode impedance. So we use this, and then we need to know the reference impedance. Normally it is 50 ohm. You just plug in and then you will get this. So as I said before, the even mode impedance is always slightly larger than the utmost impedance. So you calculate the second one and you calculate the third one, and that's all you need to do. The rest are the same. It's just mirror. So the next one I can tell you the even mode impedance will be 52 and the almost impedance. Sorry, the next one will be this one. The even mode impedance will be 53.7. The almost impedance will be 46.76. So this is what you get. Just mirror about the middle elements. Now, when you design this filter in ATS or in UCMix or Code Studio, you will have an interface for the coupled line segment, and the interface allows you to input the frequency, the characteristic impedance, and also the even mode impedance. The interface will allow you to enter the frequency and also the utmost impedance and even mode impedance. That's all you need to know. Three elements: the even mode impedance, the utmost impedance, I should say even mode image impedance, almost image impedance, and then the frequency. That's all you need to know. Then you will get each of the lines, couple the line segment. Now I've already done that, right? By doing this, I got the figure here. This is obtained by plugging in the even mode and almost. So if I do it properly, I connect the filter in the right manner in series. Yeah, it doesn't have to be like this. You can here between this line and this line, right? You can make a U-turn. In this case, you will end up with a hairpin filter. So first we need to know how to design the conventional one. But the next stage, right, then you can consider learning how to make the shrink the filter area. So after simulation, you will get this. Yeah, but this is just it's not quite matching. Yeah, maybe there's some problem with the input and output impedance, the characteristic impedance of the input line and output line. But don't worry, we just go ahead. So I already done the layout, yeah. But you still need to do something, right? So the first line segment, you have to move up a little bit so that it doesn't short circuit with the second one, the port 2 or the second one. You have to do some adjustment here. When we actually come to the practice, I will tell you how to do it. And then that's all. That's all we need to know for the bandpass filter design. If you have any questions about this topic, please leave your questions to the comment section. Thank you very, very much for your time. Bye bye.